during the afternoon tutorial, just before the tutorial starts, we will make the groups for projects. Yeah. So we'll list out different projects and, or at least some ideas about projects, and make groups. So be there at 2 o'clock, just to be. Yeah. And there was one more which I'm. Oh, the TADA forms will, for the participants, would be at the front desk. Sorry?
Okay, thank you. So for the last talk, I will present the back and forth nudging. So yesterday I explained you that it's possible to make a very complicated scheme with the nudging, with the optimal nudging, which is probably a very good data assimilation scheme, but it's very difficult to make it work because you need the 4D var. So we will get back to the standard nudging, which is very simple, and we will improve it with the back and forth nudging. So I will first present the back and forth nudging algorithm, and then many numerical experiments and ocean models, and then some extensions to other Kalman filters, and if I have enough time, also quite new improvement of the back and forth nudging. So let's start again with the standard nudging. So remember, we have the model dx over dt equal f of x. We have some observations, y-ups, the observation operator h, and the idea of the nudging is to add feedback to the observations directly inside the model equations. So we have seen some nice properties of the nudging in a linear situation, and still the same references. So just to remember how it works, if the observations come from the true state, which is unknown, but you know the observations, and you assume that the true state is a solution of your model, then the nudging state, which is here, has a nice property, because if you take the difference between the nudging state and the true state, the evolution in time is given by this matrix f minus kh, and if you are able to stabilize this matrix, then the error will decrease exponentially in time, and then you will get the true solution after probably an infinite time. So the idea is that for operational data assimilation, you don't have very long assimilation windows. You cannot use maybe a 1 month windows for weather forecast. And that's probably what you need if you want to make the nudging converge. So the idea is that when you reach the end of the assimilation window, probably the nudging has not converged. So the only thing that you can do is from this final state, the nudging state that you get at the end of the assimilation window, maybe you can get some information back to the initial solution, initial condition, and probably try to get a better initial condition than before doing nudging. So how can we recover the initial state from the final state? The easiest solution is to solve the model, but backwards in time. Just put the final condition here and solve this equation backwards in time from time capital T to time 0. So for many standard models, this is impossible. Both from theoretical and numerical point of view, it's very unstable. So the idea is, why don't we add simply a nudging term to this backward model with the aim of stabilizing this backward integration? So we can add feedback to the observations in the backward model, So now there is a minus here because we solve it backwards in time. And if we start from the final nudging state, from the forward integration of the numerical model, we hope that we can solve this model backwards in time and then get a new initial condition. And then we can iterate, because we are back to the initial condition, so we can solve again the forward model with nudging. So this is the back and forth nudging. You iterate forward and backward resolutions. So you start with the first guess of the initial condition, for instance the background state. Then you solve the forward model with the feedback to the observations. Once you are at the final time t, you use this final condition to initialize the backward model with feedback to the observations, and you solve it until you are back to the initial time. And then you start again with what you got, just the previous iteration. Start again, forward and backward resolution. And you hope that after some time you will get a good solution. So for backward nudging, I use K prime because it's not, there is no reason why you should use the same nudging matrix for forward and backward models. But just a small thing, if you assume that you use the same nudging matrix, and if you assume that you have the convergence of the forward and backward solutions to the same limit x. So you have dx over dt equal f of x plus k y ops minus hx, and you also have dx over dt equal f of x minus k y ops minus hx. So if you take the sum and the difference of these two equations, you will get dx over dt equal f of x with the sum, and with the difference you will get k y ops minus hx is equal to 0. It means that probably you found a solution of the original model which is consistent with the observations.
There is no requirement of reversibility in the model map.
Well, at that time we assume that it's possible to do that.
It's possible to do.
Yeah, we assume that.
But what would be a mathematical factorization of that possibility?
We will see some results on models with diffusion, so that are irreversible. So it's still a very easy method, because if you have a black box model here, you can add the nudging term for almost no computational cost and no human cost. And here, the idea is that hopefully for geophysical models, the time discretization is symmetric, and so you can try, usually it works, to simply change the sign of the time step so that you have the backward model in which you add also the nudging term. But now, so we have two coefficients or matrices, k and k prime, to tune. So for direct nudging, we still use the variational interpretation that I gave on Friday, I think, which is that if you discretize in time the direct model with nudging, you can see that the nudging state is simply the minimum of a variational principle. So you minimize, it's a compromise between minimizing the energy of the system and the feedback to the observations if you choose this gain matrix. So you have the transpose of the observation operator. You can use the covariance matrix of observation error if you have it. And you have to put a coefficient in front that maybe you have to tune a little bit. So for the backward nudging matrix, you have two problems. The first one is still you want a feedback to the observations, because the idea is still to make the solution converge towards the observations. But also probably your system is irreversible, so it's not easy to compute the backward integration. So this nudging matrix K prime with the feedback term is there also to stabilize the backward resolution of the model. So if everything is linear, if the system F and H is observable, then we have seen that it's possible to stabilize F to find K such that F minus KH is a stable matrix. But then if F and H is an observable system, yeah.
Why do you want to stabilize the backward solution? All you want is that the solution exists.
Yes, but when I mean stabilize is if you have a diffusion, for instance, in the model equation, then you cannot solve the backward system. So you want to have at least the existence of a solution. So yeah.
So existence is all you need, not stable.
No. Yeah, okay. Stable in the numerical way. Yeah. So if the system F and H is observable, then minus F and H is also observable. So minus F is the backward model. And so you can find a matrix K prime such that minus F minus K prime H is has negative eigenvalues, and then you know that when you solve backwards in time your system, the solution will also converge to the observations asymptotically in time. So it's usually very difficult to find this matrix. You can find it as a solution of a Riccati equation. So it's very expensive to solve because it's a matrix equation, so you have a lot of unknowns. So usually what we take is simply almost the same matrix as in the forward nudging. So if we have the covariance matrix of observation error, we use it, and then we use the transpose of the observation operator to get back to the model state, and we have a coefficient K prime. So this one is very easy to tune, because if you use K prime equal to 0, then probably the numerical resolution will be unstable. You will get some numerical explosion. So you increase K prime until the backward numerical integration is stable. And then probably it's enough. There is no need to increase more this coefficient. First some mathematical convergence results. So for instance, we consider a viscous linear transport equation. So the direct model is here, so you assume that here there is nothing. So you have the transport, which is given by a function a of x. So it is linear, and you add some diffusion. So we assume that the observations are a solution of this equation. And then we compute the direct nudging model, which is here. You simply add the feedback to the observations with some initial condition. And then the backward nudging model is here. So it's the same. You still use the standard model. It will be solved backwards in time with the final condition that you obtain here. And you add some nudging, the feedback to the observations with a sign plus, because you solve it backwards in time. And then you can iterate. But then if we know that for one forward and backward integration, the system is stable, then you can iterate. So if we start from an initial guess, and we do one forward and one backward integration. We look at the difference between the, let's say, the true solution, because here there is no observation operator, so you assume that this is the true solution. If we look at the difference between the forward nudging state and the true solution, and the backward nudging state and the true observation solution, then there are several cases. If we use constant matrices or coefficients, it means constant in time and space. So it means that we add nudging everywhere and every time. Then the backward error, so at time 0, for instance, once we have done exactly one forward and one backward integration, is given by this exponential, which is negative, times the initial error. So the error decreases exponentially, and it's still true if the observation period does not cover the entire assimilation window. So you can reduce the, you still assume that you observe everywhere in space, but not any time, and then you change this coefficient, but it's still negative. But if you don't have full observations in space, because of the diffusion, the backward diffusion makes this model, there is no, I think there is no existence of a solution, and the problem is then ill-posed. So if we assume that everything is okay, for instance in this case, after k iterations of forward and backward.
So it's not the problem, the backward problem is imposed.
Yes, the forward, there is no problem the forward, because this one is well posed and you add something which is stable. So, but the backward is ill posed because of the because of the negative diffusion. You cannot stabilize the negative diffusion with this.
What's the goal? You are trying to determine the initial condition?
Yeah.
So your convergence is something, what the claim? Converges to
The observation state at the initial condition.
converges to the opposite. So what does it say about the initial condition? I thought you were trying to do backward to be able to recommend.
Yeah. So it's here. At the initial time, after k iterations, forward and backward integrations, the error on the initial condition is given by the initial error times this exponential, which is smaller than 1. And you can see that this will converge towards 0. You still get the exponential decrease of the error to 0, thanks to different things. So either you can use some infinite feedback to the observations by using very large k and k prime. So it means that you simply replace the state by the observation. Place infinite time for the asymptotic convergence by infinite number of iterations in a small assimilation window. And you get almost the same solution as if you were able to go up to the infinite time. So it's possible to study the observability condition because if you remove diffusion, then you can only observe partially in space. If there is diffusion, then you need full observation in space. So here I remove the diffusion, and I consider this simple linear transport equation with the nudging term. So the idea is, for instance, if you take the domain, space domain is 0, 1, and it's periodic, we assume that we observe only half the domain, between 0 and 0.5. And the idea is it enough? Can we have the convergence of the solution? So I assume that the observation or the true solution is 0, and I start with a sine function. And so it's very simple. I use speed equal to 1. And so here in green, you have the sine function. So I will get back to the initial time. So in green you have the sine function. So the space domain is periodic. So the sine will go to the right and then reappear on the left. So the green one is the solution without nudging. So you simply transport with a constant velocity. So the green one is simply moving to the right with a speed 1. And the blue one, we add nudging on the left side here where we have observations. And here there is nothing, no observation, so no nudging term. And you will see that the solution is corrected on the left side, but not on the right side. But with the transport, once you corrected the solution here, it will move to the right. And then this part here, which is not corrected because there is no observation, will move there, and then will be corrected also. And so we will see that you have the time here, after time 0.5, all the solution has been corrected at least. You see, so on the right there is nothing, the blue doesn't move, and on the left the blue is going up to 0 or down to 0. So this is one forward and one backward. Okay. So the idea is that after time 0.5, all the solution has been corrected at least somewhere, because you have seen everything. If you observe here, then you will not miss anything if you wait until time 0.5. Simply because you observe half the space domain and the velocity is 1. So we can do the same for Berger's equation without viscosity. So it's the same. We start with a small sine function here, and the true state is 0. And on the left, you have some correction, but not on the right. But thanks to the transport, you get some correction also on the right. So the observability condition now is capital T should be at least 1. Then here I went up to 2, and there's still one forward and one backward solution. So once more. So there is correction here, and then thanks to the transport, there is some correction there also, because this is moving to the right and this is moving here, and then it becomes, you get the correction also. And near time 1, you have the correction here also. So everywhere you get some correction. It's periodic. Yeah. And so we can see that the idea is that if you use the characteristic curves, for each starting point, you need that the characteristic curve will lie at least strictly positive time inside the support of the of K, which means that you will observe it at least for a strictly positive time. And so for linear transport equation, the observability condition is T is at least 0.5, and for Berger's equation, you can see that there is a correction here for at least T equal to 1.
You obtain the theoretical observability condition
Here,
by looking at the observability matrix until the rank is called.
Well, here you can simply use characteristic curves, and it's easy to see that the observability conditions raise this. And so your solution should cross the zone where you have observations, where you observe. And then for constant transport equation, it's easy to see that you have this for T larger than 0.5. And here it's only a numerical observation because we were unable to find it. So some numerical experiments. I start with a shallow water model. So it's a 2D model. with so it's still the same model as before. It's, you assume you have a huge square swimming pool instead of the North Atlantic Ocean. So there is almost all physical stuff inside. You have the vorticity, Coriolis force, the gravity, which is here, hidden B. Then you have some wind stress, some friction, and some viscosity. So everything. So h is a sea surface height, and you have two components of the velocity. So this is an example of model run. So this is the ocean. So here it's the sea surface height. Green is the mean height. Blue is lower than the mean, and red is larger than the mean. So the idea is that you have some main current here. So for instance, the Gulf Stream in the North Atlantic Ocean. And water is going like that, and then there is a recirculation over here and also here. And so the Gulf Stream is moving, and you have some nice vortex. So it's a 2,000 kilometer domain. The assimilation period is 15 days, and then the forecast is 45 days. So it's, usually we start from the initial, the beginning of the assimilation window. So there are 15 days of forecast during the assimilation window, and then 45 days of real forecast in the future. So I used twin experiments. So I generated the observations with this model, and I extracted observations on this SSH only, every 5 grid points in each direction, and every 24 hours. So trying to get some realistic amount of observations, and there is nothing on the velocity. And then I add some noise. For a background, I use the true state of the model, but 1 month before the beginning of the assimilation window. I add also some noise. And okay, so let's reduce it. At the beginning, this is the background state, and we run 5 iterations of forward and backward nudging. So just look at the way the water is going. So now it's backward, and then forward again. I hope you see that it's going on one side and then the other way. So here water is going back, now it's going in the forward way. So you can see the distribution of the observations with this the location where the corrections are. So 5 iterations, because it's enough after nothing happens. And then probably it's the final one. And then we will be back at the initial condition. So I stop here. And we can compare. We can compare it with the true solution, the one I used for generating the observations. This is the background state. So this is what you have if you don't have a data assimilation scheme. And this is what the 4DVAR does in 5 iterations. I should have stopped it before because, so okay, we can compare these two schemes because 4DVAR, you iterate the forward model and then backward the adjoint model. And for the back and forth nudging, you iterate forward and backward plus nudging. So both algorithms consist in iterating forward and backward models. So we should compare the number of, if you use the same number of iterations, it should be almost the same computational cost. But in fact, the adjoint is much more expensive than the standard model, usually 3 to 5 or 8 times the forward. So 5 iterations here, it's 10 resolution of the forward model, and here probably only 2 4D iterations would be around 10 model runs. But then I've done 5 iterations, so it's a little bit more expensive in time, just to see. So of course the 4D has not converged yet, and you can see what you get after 5 iterations. And then with all these initial conditions, we can run the model without anything, the standard direct model, to compute the forecast. So first during the assimilation window, and then real forecast over 45 days. And at the end of the forecast window, so this is the true state 45 days after the assimilation window. This is what you get if you don't have a data assimilation. So you can see that almost this is not there. This one is also misplaced, and so on. With the 4D var, it's not much better. And with the back and forth nudging, we have a quite good forecast. Well, at least for the SSH, and then for the velocity, it's not exactly true because the Gulf Stream is not located exactly at the correct place. And if you run, I think, nearly 3 or 4 times more, 16, I think, iterations of 4D var, you get convergence, and then you get something closer to this state. So just to show some convergence results of the root mean square error. So it's a relative RMS for the 3 variables, sea surface height and velocity. So here there is no noise on the observations, and you can see, so this is the assimilation window, and you can see that the error decreases in time on the forward run, but also on the backward run, and so on. So you can see that there are some strong oscillations at the beginning because I don't smooth the nudging term. So I add the correction only at the observation location. So there are some gravity waves. So that's bad, but it's easier for me. And for the backward, I use the small coefficient K prime, which is exactly the smallest one for stable, because if you look here, you can see that there is beginning of the instability. So if the assimilation window was a little bit longer, then it would be unstable. But then you can increase a little bit the coefficient. So here I compare the still the relative root mean square error between several data assimilation schemes. So here is the assimilation window, and here the 45 days for the forecast. So the back and forth nudging is there. So it converges in 5 iterations. And you can see that the initial condition is not very well identified, but then you get very good forecasts. So what I showed also was the 4D var with 5 iterations also. So this is this one. The initial condition is better, but then the forecast is worse. So what is interesting is that the 4D var needs 16 iterations to converge. And the solution is this one, I think. So the one here below, and then it goes above. So 16 iterations is much more than 5 iterations of BFN, because 5 iterations of BFN is almost 10 model runs, whereas 16 iterations of 4D var is probably 80 or 100 of model runs. And you also need an efficient optimization algorithm to minimize the cost function. Okay. So the idea is that probably, as we have seen that the BFN converges very in a few iterations, the idea is to pre-process the 4D var. It means that you start with your background state. We perform 2 iterations of back and forth nudging, and then the new initial state that we get, we use it as the new background state for the 4D var. So here we have done 2 iterations of back and forth nudging and then 3 iterations of 4D var, and we almost get the same solutions as the converged 4D var. So we reduced drastically the computational cost, but we get almost the same solution. So a more complicated ocean model. Well, in fact, I've done work on the quasi-geostrophic before shallow water, but so this is more or less a 3D ocean model. Well, in fact, it's 2D and half. So you just have several layers of 2D ocean models. And on each layer, you still have almost the same equations as in the shallow water. You have the stream function, the vorticity, force, and then some dissipation at the bottom of the ocean, and some lateral friction with the 6th order differential operator. And then F is the wind stress at the surface. So we assume still that we have some satellite observations, for instance coming from Topex Poseidon or Jason. And the observations of the sea surface height could be related to the upper stream function psi1. So we assume that we have some observations on the upper layer only, and they are sparse in space and time. The control vector is the initial state on all layers. And we can try the back and forth nudging on this model. So here is the convergence of the BFN scheme. So here there is no noise on the observations. And you have the relative RMS difference between the nudging state, the BFN state, and the true state. So it's the difference over all the layers. Well, I used only 3 layers for the numerical scheme. So here it's the difference between 2 consecutive iterates. So after nearly 20 iterations, the iterate does not move anymore, so we can say that there is no need to make more iterations. And here it's the difference between the BFN state and the exact solution. So you can see that you have some convergence also after 20 iterations. A funny thing is that you can compare the decrease of the cost function and the gradient of the cost function. So we have the cost function and the 3 gradients on each layer. So here it's the 4D var. The goal of the 4D var is to minimize the cost function. So the cost function decreases. Whereas the nudging, the goal of nudging is not to minimize the 4D var cost function, but as we have seen, it's a compromise between minimizing the energy of the system, but also the distance to the observations. So in some sense, you minimize also the distance to the observations and then the 4D var cost function. And you even minimize it more efficiently than the 4D var, which is quite funny. So here it's the same with noisy observations. You still have the convergence of the back and forth nudging algorithm, but you need probably a little bit more iterations, and the RMS error at the end is larger than if there is no noise. So this is the comparison for the forecast. So you have the assimilation window here, 5 days, and then 15 days of forecast. So probably it's a little bit short. It's a short window. But then the idea is that on this model it has been proven in the late 90s that with observations only at the surface, you can correct all the layers. So the idea was to see if it's also possible with the back and forth nudging, because you correct only the observation, the upper layer with the observations. So we can see that for the second layer it's still true, but then for the bottom layer the correction is not very good. Probably the assimilation window is too small to let the model propagate the correction towards the bottom, because there is some vertical diffusion in the model, but you need some time. And we added also some model error, so we used a different model for different model parameters for generating the observations than the model that we use for the assimilation. And it still works quite well. Still everything is okay. So this is so more recently we studied more complex model, which is the full permutation model. So we start from the Navier-Stokes equations with the velocity u and the pressure p. We use two active tracers, temperature and salinity. So here you have the equations for the heat and salt. So it's simply a transport equation plus some diffusion and forcing term. So we assume that the fluid is incompressible, and you need the hydrostatic equilibrium to link the density with the pressure, the vertical pressure gradient. And you need one more equation to close the system. So it's an ad hoc equation on the density. So it could be the constant function, or you can assume that it's constant on each layer or whatever. And there's a free surface formulation. So the height of the sea surface height is given by the divergence of the velocity field at the surface. And then with this you can integrate the surface pressure, because you have the this equilibrium. So if you know the height of the surface, you can integrate and get the surface pressure, and then integrate all the other equations. So everything is coupled. It's quite difficult to solve that, but we used NEMO, which is I think Nucleus European Model for Ocean. I'm not sure of the acronym, but it's a quite new ocean model which is developed in Europe, mainly between UK and France, I think. So it's still like the shallow water model. It's a double gyre circulation between closed boundaries, so still square boundaries. And we use a sinusoidal zonal wind to force the model. Still twin experiments. You generate the observations from a reference frame. You extract the observations. So here we get SSH along satellite tracks, and also some observations of temperature on a regular grid, which is more or less similar to the Argo float network. So this is inside the PhD of Patrick Bonsard, who is expected to defend this year. So here you can see the tracks that we used for the SSH, and here the location of the Argo floats for the temperature. So the SSH is every 10 days you have this or you can do every 2 or 3 days some of these tracks. And here we have the vertical profiles of temperature at these points every 18 days. So this is the error between the BFN state and the true state for the temperature and one component of the velocity. So the assimilation window is 20 days, and there are 6 iterations of BFN. So you can see the error decrease in forward and backward nodes along the iterations. So here it was one of the first experiments. So he used full SSH observations every day. The point is that we only use nudging on the temperature itself with the observed temperature, and there is a nudging term on the SSH equation with the SSH. So there is no coupling and there is no correction on the unobserved variables. And here is the same with realistic SSH observations, so along the tracks and with noise. So it's the error is increased, but still you see the decrease of the error during the iterations. So it's only partial results, but we have a new PhD student that is going on. So what we have done for nudging, we can imagine do the same for almost any Kalman filter. Because the idea to use the model and then correct with feedback to the observations, so either a nudging term or a Kalman correction term, we can imagine do the same in backward node and iterate. Okay, so we can imagine that after doing a Kalman filter, at the end of the assimilation window, you get backwards in time, you use the model, the backward model to forecast between 2 observation times. Once you have the observation, you use Kalman filter to correct, and so on, back to the initial time. And so you can iterate. So the idea is that if you use the full Kalman filter, it's very expensive to do it once, so you will not do it twice or more times. So the idea is to use a faster filter. So for instance, we use the SIG filter, which is a Kalman filter. It's an extended because it works with nonlinear models. It's singular because you reduce the dimension of the covariance matrices, and evolutive because you can start with almost any approximation of the covariance matrices, and then at the end you will get some good approximation. So the idea is that you replace all the covariance matrices with low rank approximations. So these matrices are the size, if you consider 1 billion points, these matrices are 1 billion by 1 billion, and the idea is to replace them by matrices of rank maybe 20 or 50. So for this, we use the singular value decomposition. So you can, at the beginning, well, any covariance matrix is real and symmetric. Then you can diagonalize it like this with the same matrix here, with the transpose here, and this diagonal with the eigenvalues that are positive. So you can take the square root of the eigenvalues, and then at the end you get a matrix S, which is like that. Well, you get a full matrix at the beginning. And the idea is that the eigenvalues are decreasing almost exponentially with the size of the matrix. So you can keep only the very first eigenvalues, the largest eigenvalues, with the corresponding eigenvectors. So you just keep a few tens of eigenvectors with the square root of the eigenvalues. And the same thing on the transpose here. So if you multiply this by this, you get a full matrix with a rank 50 instead of full rank. So S is this one. It's 50, for instance, by 1 billion matrix. And S times S transpose is a good approximation of P. And if you take R, so 50 equal to N, it's no more an approximation. You have exactly the square root of the matrix. So you decompose all the covariance matrices like this, S transpose, and the dimension of S is the dimension of the control vector, for instance 1 billion times R, which is of the order of 50. And then you can take all the Kalman filter formula and replace P by S transpose. And for instance, when you update the covariance matrix of analysis from the covariance matrix of forecast, if you replace PF by SF transpose, you can rewrite PA like that. And inside here, the matrix here is R by R matrix, so it's a very small matrix. You can take the square root and put half on S and half on S transpose to get SA transpose for almost no computational cost, because you simply have to take the square root of 50 by 50 matrix. So all the propagation and all the computations of the covariance matrices are easy and very fast. So here even I said 10 to 30 nodes. Then if you want to get the forecast covariance from the analysis covariance, the idea is that for each of the vectors inside the S, so for each of the model node, you compute, you run the model, you take the forecast from the analysis, but you take also a forecast from the analysis plus this vector, and the difference here is almost the tangent linear model times this vector. So this is what you want, the corresponding vector for the forecast covariance matrix. And so here's the SIG filter. It's almost like the Kalman filter. So you lose some time here because you need to compute some forecasts and model runs for each column of S. So if you have 50 modes, you have 50 model runs. But then the computation of the covariance matrices here is at almost no cost. So the idea is that with this filter, which is not very expensive, you can iterate forward and backward resolutions of this filter. So a student did that on a shower water model. It's almost the same. The assimilation window is 30 days. There's a daily assimilation of SSH along satellite tracks. So here there was no dynamical propagation of the errors, so it means that roughly the SIG filter is some optimal interpolation. So here is the, for instance, what you can assimilate one day, the SSH which is available every day. So here is the, on the right, it's twin experiments. On the right you have the true SSH, and on the left the identified SSH after, so here 0 iteration, so it means it's the background state. Then after 2 iterations, there's some correction of the Gulf Stream. After 4 iterations, and so you can see here the decrease of the SSH error during the assimilation window with the iterations of back and forth SIG filter. So you can recognize it's a Kalman filter. You have every day a correction, So forecast and prediction, correction, and so on. It's the same in the backward resolution. You have the forecast and the correction. And the correction is simply the same, just apply a filter to make some interpolation between your model state and the observation. The only difference is that for the forecast between two observations, you use the backward model. And it works also, so it's quite nice. So, still some time to show you some, let's say, improvement of the back and forth nudging for our geophysical problems. So diffusion is a difficult problem in when you want to solve backwards in time your model, because you have instability. Hopefully, so we have seen, for instance, that with Berger's equation, the problem is ill-posed, and then numerically it's always okay, because even if theoretically the Laplacian has infinite eigenvalues, when you discretize, you have finite eigenvalues. So you can always take large enough k in order to balance these positive eigenvalues to get a stable model. But then it's not very physical, because you have to increase a lot the backward nudging coefficient, and it's not very good. So the idea is that we have discussed with geophysicists, and the idea is that theoretically the equations are diffusive free. For instance, in weather forecast, at least in Meteo France, they use Euler's equation and not Navier-Stokes. So there is no diffusion. But then, if there is no diffusion, for a hyperbolic system, it's quite difficult to solve numerically. So the idea is that either you use a diffusive scheme to solve your equations, otherwise it could be unstable, you can have instability in your numerical integration, or you add a small diffusive term inside the equations to have a more stable system that you can integrate. Also, the diffusion term is there to take into consideration some subscale phenomena, because you discretize along a grid. Okay, so your space looks like that. And if, for instance, for a meteorological model, you have 10 kilometers between two grid points, your model cannot take into consideration what happens inside a cell. But then inside the 10 by 10 kilometers, you can have huge storms or very energetic things that your model cannot take into account. So the idea is to add a small diffusion term. For instance, on the quasi-geostrophic model, it was a sixth-order differential operator, to try to take into consideration what happens inside the cell. So the idea is to assume that the original model, the physical model, has no diffusion. So it's a reversible model. So we can write it like this. dx over dt is equal to f of x, where f is diffusive free. So the standard back and forth nudging algorithm is there. You have the nudging, the feedback to the observation in the forward and in the backward models. But then you will have some problems with the numerical solutions, because it's a hyperbolic system without diffusion. So probably either you will get some instability, or you will have to use a diffusive scheme. So let's add some diffusion to the model. So here we assume it's a Laplacian, but it could be something else. And f is diffusive free. So the idea is that the observations should be a solution of this model. Okay, the observations for weather forecast should be a solution of some kind of Euler's equation without viscosity. But then you will use a model with diffusion. So the diffusive back and forth nudging is the following. On the forward resolutions, you use the physical model. You add some diffusion to stabilize numerical integration and also to take into account the subscale phenomena. And you add the feedback to the observations. For the backward model, you use the backward theoretical model, physical model. You add also some diffusion with the good sign, the stable diffusion, still to help you to solve numerically this hyperbolic system, and also to take into account the subscale phenomena, which could be also reversible. And you also add the feedback to the observations, also with the correct sign to have the good feedback. Okay, so you have a minus here and here, because this is a backward model. So if you make a change of a variable change here to get back to a forward model, so instead of solving it backward in time, you simply use another time variable, which is capital T minus T. So you simply dtx, you change the sign, and then you get back to good diffusion, good feedback to the observations, and backward model, minus f. So the only difference between the forward and backward resolutions is that you change the sign of the physical model, which has no diffusion. And now in the backward model, the diffusion has the good sign. It's a good diffusion, it's not a negative diffusion. So it's easy to solve this equation, even with nu close to 0, because and k or k prime close to 0 or equal to 0, because it's a stable model now. And you still get your physical interpretation of the diffusion. So now, for symmetry reasons, you can use k and k prime with almost the same values, and there is no problem for stability.
But numerical discretization may actually increase some function. Why do you need additional?
If there is no, well, you can simply.
Of course, it depends on the scheme you use.
Yes, but for instance, you take Berger's equation. If there is no viscosity, there is always some trouble with your scheme. So the idea is that for Euler's equation, you cannot use very complicated schemes. So if there is no diffusion, that you add, or if you don't use a diffusive scheme, probably it will not work. So usually people use diffusive schemes.
It brings back to the question, what is the true definition of a backward system? I tend to think of a backward system or a backward as something that is actually a reversible. You don't have any separation of the model now.
This one is reversible. So the backward model is simply this.
So, my question is, in what form your results are strengthened if you assume your model F is reversible as opposed to non-reversible model?
Then you can choose any nudging coefficient, even 0. You know that everything will be okay. That's the point. So you can study the theoretical convergence in a very easy case to see what happens, what we get at the end. So we suppose that everything is linear, once again. So the model operator F and the observation operator at H are supposed to be linear. And we consider just one forward and one backward integrations. So the idea is that from the initial condition of the nudging state, and also from the knowledge of the initial observation, assuming that the observations are a solution of the direct model, we can make one forward and one backward integration and get the new solution at the initial time. So we need to study this operator. The idea is that this operator is linear in both x1 and y-ups, so that there exist two linear operators C and D, such that the solution you get after one iteration is a linear combination of the initial condition and the initial observation. So you can iterate this, because this is the second, because we assume that the observations are a solution of this. We assume that there is a reference solution which is a solution of this model, and you observe it through H. So, well, okay, it's not, it should not be y-ups here, it should be x. It should be the initial condition of the true state, reference state that is observed. So this is one iteration, so we can iterate and compute after k iterations. So namely the initial condition, the background state used to initialize the algorithm is multiplied k times by c, and then the observations multiplied by d, and then by this sum here. So the idea is that we should look at c to see if the spectrum of c is well, strictly included in -1, 1, then ck goes to 0 when k goes to infinity. Okay, it's a contractant operator. So this sum converges to the inverse of I minus c, and then so this goes to 0, this goes to the inverse of I minus c, and then at the end we get convergence to this solution here. So okay, but what is C, what is D? So let's take a simple example. Take the linear transport equation. So we assume that there is no diffusion. We assume that we have good properties on the velocity. So we assume that the observations are a solution of this system here, and then for stability and subscale modeling reasons, we will use this numerical model. We will solve numerically this system with some small diffusion, either like that or with a diffusive scheme. So we assume that the observations are a solution of this equation without diffusion, and we solve this from the back and forth nudging with the diffusive BFN algorithm. So in forward mode, we have plus the transport term, then we add some diffusion to stabilize numerically, and some feedback to the observations. And then in backward solution, so here we change the time to get everything in forward mode. So we reverse the model, it's minus A, the backward model, and we still have diffusion and feedback to the observations. And we use the same feedback to the observations. Then we can make, so the only difference between the forward and backward resolution is that simply you change the sign of the transport function. So we can make some energy estimate. So here it's not exactly U, it should be the difference between the solution that you compute and the observations. But then the idea is that the diffusion is good, both in forward and backward mode, so this is negative, you can forget it. And then you can control the energy by this term, which is negative if you take the nudging coefficient larger than the infinite norm of the derivative of the transport A. So if k is large enough, this is strictly negative, and then the energy decreases exponentially in time. So you have convergence. In the special case where you use constant transport, you still have convergence, of course, because it's very easy because here it's equal to 0. So for any non-negative k, you have convergence with the exponential decrease. And at the end, the solution is this one. You have convergence of the forward and backward solutions to this solution V infinite, which is a solution of quite well-known equation in image processing, because it's so in image processing, when you have noisy image V, you can solve this equation, and then what you get U is a smooth image close to V. So you simply regularize the solution V with the Laplacian operator. So here it's the same. You have the coefficient nu over k, which is the degree of smoothing of your operator. Yeah, you use some coefficient here, and then epsilon is nu over k here. So the idea is that we should converge not to the observations, but to the smooth observations smoothed by the Laplacian, which is probably a good thing if the observations are noisy.
Go back to the previous one. So convergence is for forward.
No, well, it's the same because forward and backward are the same. You just change the sign of A, then there is no, here A is either plus or minus, but there is no, now there is no difference between forward and backward. So, if we try with, so the observations are in red, so it's a linear transport equation. It's still a periodic domain. So the initial time you have the positive part of a sine function. So you can see that it's not smooth here. And we use these observations. And we start with the background state equal to 0. And so if you run your transport equation, this positive sine function will move to the right and then reappear on the left. So if we apply the diffusive back and forth nudging, we can plot the decrease of the error during time along the iterations. And here it's the same in log scale. So we can see that we have a nearly constant decrease with a constant decay rate, which is exactly given by this ratio. And at the end, you converge to the blue solution here, which is exactly the solution of this equation here. So you smooth the red curve with the Laplacian, so it goes down here, and then here you have the smooth curve. You can do it also for Burger's equation, so without diffusion. So there will be a shock for sure after some time. And it's the same, the diffusive BFN is in the forward mode you add the diffusion, small diffusion, and feedback to the observations. On the backward system you add the diffusion and the feedback to the observations. So here it's written in backward way. If you want it in a forward, you just put plus here to have the good diffusion and feedback to the observation, and you just change the sign of the physical model, the derivative of u square. So here's the initial condition is a sine in blue, and then after some time, so this is moving to the right, because it's a nonlinear transport equation and the velocity is given by the solution itself. So if it's positive, it's going to the right, and if it's negative, it's going to the left. And so after some time, there will be a shock. The solution will be like that, and then the gradient of the solution goes to infinity, and there is a shock. So you can add some diffusion to stabilize this. And so it's still the PhD students that compared this new diffusive BFN algorithm with, it's not a 4D var because it's a 1D problem, so let's say a 2D var, 1 plus 1. And so you have different, so here's the observations, one every 4 or 10 grid points, and one every 4 or 10 time steps, wave out or wave noise. And you have the number of iterations to get convergence of the algorithms and the relative RMS error at the convergence. So the idea is that you still get the extremely fast convergence of the scheme, even faster than with the standard BFN, because there is no problem with the backward resolution. And the RMS error is smaller than with the variational algorithm at convergence. So this is of course a very simple, and here is the forecast. So assimilation window and forecast window. So you have the RMS difference between the BFN and variational identified states and the true state. So you can see that still the initial condition is not very good, but then after some time you have a good forecast. So here you have it's a small shock that appears at the beginning, and then you have some physical correction of the model. So to conclude, well, it's almost the same conclusions as for both diffusive or non-diffusive back and forth nudging. The idea is that you have a very easy implementation, almost as a little bit less easy than standard nudging, but much easier than optimal nudging. So there is no linearization, no adjoint state, no minimization, no huge covariance matrices, almost nothing. But still it's very efficient in the very first iterations. So you have very fast convergence and for a low computational and memory cost, because you don't need to store anything, there is no adjoint, there is no huge matrices. There is some interest for stabilization of the background model, or for if you assume that you have, so it's not data assimilation, but if you assume that you have some model which is unstable, it could be interesting to be able to stabilize it if you have some observations of your system. And we have seen that probably you could perform a few iterations of BFN to improve a lot the background state before using a 4D var or Kalman filter. The idea is that the cost here is extremely small, and you can divide by 2, 3, or 5, maybe the number of iterations, or 4D var iterations after to get the same result. So still a lot of work. So mainly on the full primitive version model, the idea is that probably we have to correct the other variables, mainly the velocity, from the knowledge of the SSH. So almost what's like in the shallow water model, correct the velocity with the gradient of the height, for instance. And also try to improve also the, well, at least backward, but also probably forward nudging matrices. Because we know that we can get some kind of exact stabilization of the model with the solution of a Riccati equation. So some people are working on a very fast resolution, approximate resolution of Riccati equation to get very quickly an approximation of the solution, that could be a better choice for the nudging matrix.
Because, I mean, physically, you're looking for the state of the system at this time that gives you this at the end time. And presumably the idea of using viscosity and so on to parameterize small-scale processes, that sort of creates an energy cascade which drains energy from this, right? And by doing it backwards and giving sort of positive diffusion backwards, you're implicitly kind of adding it.
Yeah, what I've seen with the shallow water model is that the diffusion is very, very small, and then if you plot the energy, you almost don't see anything. So the nudging term is gives more or reduces more the energy than the diffusion. So if your model has a lot of diffusion, then for sure you have trouble. But for shallow water model or even a full primitive ocean model, there is almost no problem with the horizontal diffusion.
Right, it's just a question of whether you can claim that it physically represents parameterization of small grid scale processes.
I don't claim it. It's some colleagues of mine. Yeah, but some colleagues in Grenoble, geophysicists, they say that it's like that. So I can give you the names.
So you're repeating what I just said.
Yeah.
But they're geophysical.
Yeah, so I hope it's true. Yes. Yeah. Well, there is no problem with the wave equation because it's well posed. So yeah. Yeah, there is no problem with the.
What is the goal of the backward?
To be able to do nudging some more time because the assimilation window is very small, so you will not get convergence because it's asymptotic convergence, the standard nudging. So you have exponential decrease, but after a few days, the decrease is not very interesting. So you have to do some more nudging. So the idea is to get back to the initial condition to do nudging again. And then why not doing nudging also during the backward? But for a wave equation, for instance, I've seen a student did the forward with nudging and the backward without, for instance. And it works here.
But they can use the nudging.
Yes.
Backward without nudging.
For the wave equation. Yeah. For a shallow water model, for instance, after 2 or 3 days, it, you get some tsunami.
Let's say you're looking at an atmospheric model, putting on linear with all the forces.
Yeah.
And I have this rainfall term which occurs between T and something like 30. And you have to go backward in time. And I have to nudge back. How will I handle it?
Well, actually, I only worked with ocean models, so probably in the next day. There is no rain, yeah, hopefully. So that's the point that we have to study. But it's difficult in France because for atmospheric models, almost everything is in Meteo France, so we don't have access to models. So, whereas for ocean science, it's more colleagues at the university. So, but try to make the rain go backwards. Yeah.
Okay, so yeah, we'll diffuse now. Try to do a reverse diffusion, maybe a little bit earlier, just before 2, so we can start talking about the project. And before his tutoring, I guess Act 2, so we can do it Act 2. Well, no, actually Act 2, yeah, I think right now, yeah. So Act 2 is the thing.